Hello everyone, my name is Jourdan and I will be presenting our work on the computational design of self-shaping surfaces by 3D printing onto stretch fabric. This was done in collaboration with Mélina, Skouras and Adrien Bousseau from INRIA and Etienne Vouga from the University of Texas at Austin. The method consists in taking a piece of textile and then pre-stretching it as uniformly as possible. We then use a 3D printer to deposit plastic directly onto the stretch fabric so that when we release the textile, for example by cutting around it, it automatically pops out of the plane. Our goal is to solve the inverse design problem of finding the optimal pattern to be printed onto stretch fabric so that the fabricated shape self-deploys into a surface which is as close as possible to the input. 3D printing onto stretch fabric as a technique for creating self-shaping textiles has been investigated before, but it was mostly focused on designing these sparse networks of closed curves which only allows them to reproduce specific surfaces. If we look at one such closed plastic curve, here depicted in black, the tensioned fabric will try to minimize its area so the end shape looks like a minimal surface. The same principle applies to these more complex examples, which are like piecewise minimal surfaces with negative Gaussian curvature. In a previous work of ours, we showed it was possible to obtain convex surfaces with positive Gaussian curvature by printing small and disconnected elements instead of closed curves. We also highlighted the importance of modeling the bilayer made out of a stiff plastic layer on top. We also highlighted the importance of modeling the bilayer made out of a stiff plastic layer on top and the tensioned fabric below. The forces applied by the fabric below will cause the bilayer to curve up, and the curvature obtained along this bilayer is a function of the thickness of plastic. The thinner the plastic layer is, the less resistance is opposed, and therefore the more curved the resulting bilayer is, and vice versa. This technique allows us to obtain a wide range of positive normal curvature, but to obtain negative values, we have to print on the other side of the textile. We will later see how it is possible to do this. This bilayer effect is great for controlling the normal curvature through bending, but to modify the Gaussian curvature and move away from developable surfaces, it is necessary to modify the metric. In this work, we focus on printing patterns of parallel straight ribbons. These have the property of causing the sheet to morph anisotropically. When we release the textile, we can see that along the ribbons, the shape is still as wide as before, because the plastic resists deformation. And we say there is a distortion, a ratio of lengths equal to 1. In the perpendicular direction, however, there is a larger amount of distortion. What's interesting is that this amount can actually be controlled by controlling the density of ribbons. If there are more ribbons on this square, the distortion will be lower. As I mentioned, the distortion along continuous curves is equal to 1. It might be a bit constraining to force this distortion value to 1 everywhere, so a way to relax this problem is to print dashed lines instead to leave some space for the fabric to shrink. And to avoid creating weak structural points, we can lay out the curves in an alternating fashion so that the gaps don't align. To sum up, in this work, we generate a pattern of parallel ribbons, which allows us to control both bending through the bilayer effect and metric distortion by controlling the amount of space in between each ribbon, both along and across the ribbons. So to solve this inverse design problem, there are 3 main steps we need to follow. First, we need to find a flattening of the target 3D surface which matches the fabrication constraints. Then we can compute the optimal ribbon layout to be printed so that the prescribed normal curvatures and metric distortions are reproduced. And finally, we will see how to actually fabricate it, and in particular, how to print on both sides of the fabric in an efficient and repeatable manner. So to compute that flattening, there is a few requirements that we need to follow. The first one is that the curves should be aligned with principal directions of curvature. The reason for that is because principal curvature directions are the only directions on a surface that are torsion-free. Since we are printing ribbons, the ribbons will naturally try to resist torsion, so if we try and print curves that don't follow principal directions of curvature, like in this cylinder, the ribbons will straighten out and distort the end surface. The second requirement is that the distortions induced by the ribbon pattern that we are going to generate have to stay within some specific bounds given by the fabrication constraints. If we look at one point in this torus, for example, we can compute the principal curvatures, and we know that if there is a ribbon passing through that point, it will have to follow K1, which is the direction of maximum curvature. So along this direction, when we flatten the surface, the ratio between infinitesimal lengths, so sigma 1, cannot be smaller than 1, because 1 means there is a continuous curve, and it cannot be larger than some value because we don't want the gaps between the ribbons to be too wide. And we have the same type of constraints in the perpendicular direction with sigma 2. To fulfill these requirements, we employ a local global algorithm which has been used in previous work for programming an anisotropic metric into sheets of material. This local global framework is very common for ARAP parametrization, for example. The idea is to alternate between a local step where every triangle is modified to fulfill the given constraints and a global step where we recover the mesh topology. This local step is applied to every triangle, so we can look at one triangle specifically, and the idea is to find a deformation of the triangle from the input 3D mesh which is as close as possible to that same triangle which was obtained from the flattening in a previous iteration. So here we can see them overlaid, and here the principal directions of stretch have to be aligned with directions of curvature. So we find the best matching stretch values in the two orthogonal directions. One advantage of this type of local global approach is the very fast convergence rates that we can get. The local step can be computed in parallel and implemented on the GPU, which means that on this example, it will only take a few seconds to converge. Now onto the pattern generation part. So to lay out our ribbons on the surface, we use the stripe patterns algorithm, which generates a pattern of curves whose spacing depends on local frequency values. Here, the frequency values are computed from the distortion values of the parametrization, and the stripes follow a specific directional field, which is here the directional field of principal curvatures. We do this with one directional field and one set of distortions, and with the perpendicular directions and another set of distortion. And we can combine the two to have this sort of grid of stripe patterns. We use this grid to align our ribbons. We position the ribbons at each curve intersection. Now, one issue here is that we don't have this staggered ribbon pattern that we wanted to have previously, and so this might create an alignment of gaps which will cause some structural problems. So instead, we generate two different patterns of stripes with half the frequency and a phase shift of pi. Positioning the ribbons at the intersection of either the yellow curves or the blue curves, we obtain a staggered ribbon pattern. The last information we need for generating this pattern to be printed is the thickness of the individual ribbons. To find this thickness, we can look at a surface element which is representative of the staggered ribbon patterns we generated. Such a pattern we deploy into a cylinder whose curvature is a function of the thickness of plastic because of the Bailey effect, but it is also a function of the spacing between ribbons or the amount of tensioned fabric in between. To invert this function and find the thickness as a function of the local curvature and spacing of ribbons, we print various samples and measure their curvature so as to build a database of varying curvature, thickness, and spacing. and we just use that database to look up the thickness as a function of the local curvature and spacing. Now on to the last step, which is the fabrication process, where I will explain how it's possible to print on both sides of the fabric. And the reason why we want to print on both sides of the fabric is because of this type of situation where if we want to place ribbons on the surface, some will have positive normal curvature and some will have negative curvature. Here we distinguish between the two with the colors red and blue, so that they have to be so both sets have to be printed on both sides of the textile. To be able to easily print on both sides of the fabric, we designed this system where the fabric is clamped between two identical frames and the ensemble sits inside a base platform which prevents any sliding motion. To stretch the textile, we draw a scaled down rectangular shape which we will try to align to the frame. On each corner of that rectangle, we attach these small removable elements which will be securely locked on the outside of the frame. The initial position of these corners is chosen so that we get the right amount of strain as the one we used in the algorithm. Once we have stretched the textile, we can put the frame onto its base platform and begin printing all the ribbons we identified as having positive curvature. Once this is done, we flip the frame and start the second printing sequence, which corresponds to the ribbons with negative curvature. Finally, we can cut around the shape boundary and let the object self-deploy. Now let's look at some results. So here we compare the input surfaces and the fabricated ones. And we used our method to reproduce a variety of surfaces with both positive and negative Gaussian curvature. And in many cases, the surfaces had a mix of both. You can look at the paper to see also more quantitative comparisons between the inputs and the fabricated results. Because we're working with textile, which is a very soft material, sometimes the surfaces have a hard time supporting their own weight. In this case, for example, we applied a textile hardening product on the surface of this architectural model to make it stiffer. Instead of architectural models, we can also imagine applications for the fashion industry, for example, this skirt which has some specific folds programmed on it, or this mask. Our method is really based on following this directional field of principal curvatures, which makes it subject to failure in the case of umbilical surfaces. Here on the left, we try to reproduce a spherical cap, but since there is no preferred curvature direction, the algorithm just picks a random orientation and aligns all ribbons with it, which is maybe not the ideal solution. Another issue we had is more related to the fabrication process. There are a lot of imprecisions due to the printer, sometimes leaking material, or the thickness of the layers being different than expected. To sum up, we proposed a full pipeline for the inverse design of self-shaping textiles by 3D printing on fabric, which includes first a flattening algorithm based on the local global framework, then a system for generating a pattern of ribbons to be printed from that flattening and its corresponding distortion values, and finally a fabrication system which allows us to print on both sides of the fabric. This method is purely geometry based. It's based on this idea of controlling both the normal curvature of the ribbons and the Gaussian curvature of the surface. We would like to integrate a physics simulation tool into that algorithm, which might allow for more accuracy of the method and could help solve issues with surfaces not supporting their own weight. Thank you for your attention.